Thanks for joining this session. This is Perspective on Public Purpose. Really excited to have all of you joining us from different parts of the world and the United States. So this is very, very exciting. I'm very happy to be here with a very good friend of mine and great professor, Fiorenzo Manetto, that is going to be our guest. We're going to have hopefully an interactive discussion today to talk about how this unusual couple of entrepreneurs and scientists can sometimes work together and try to create something new in the field of what now we call deep tech. Some people call it tough tech. Some people call it technology that take very, very long time to develop, because most of the time they are originally invented in some laboratories, either a university or another center of research and development. And then sometimes they get actually spin off into the real world and they actually can have an impact on everyone's life. So I'm very excited to share some of the learnings from this project that a team of researchers here at the Belfer Center has undertaken. And I'm also very, very excited to have Fio's perspective to give us his thoughts on how we can actually get more of those technologies out in the world and transform some of the early stage research concept, intuition, and maybe ideas that might seem too big to be true, too far to be fetched, but maybe there is a way to try to get there. So let me introduce you, Fio, very, very quickly, and then we can move on to some of the learnings. So Professor Manetto is the Dean of Research at Tufts School of Engineering, and he's also the scientific co-founder of a company that I co-founded with him, Vaxxes Technologies. He's also the co-founder of other innovative biotech companies that are having a lot of impact from his research. Interestingly enough, Professor Manetto was also a researcher at one of the most prominent national labs, or the federally funded R&D centers in Los Alamos in New Mexico, before transferring to Tufts University. So I think he has a unique perspective that is very relevant to this research, having seen both of the worlds. As I said before, Fio has been very focused on translating his research from the lab to the world, and has done it with a very, very interdisciplinary approach. And I think he's going to tell us a little bit about that experience. What works, what doesn't work, how can we do it, or shall we even do it even more, or should research just be research, right? And I think that's a leaning question, because we really believe that we can have a big impact working with teams across disciplines. So before we start the conversation, I don't want to bore everyone too much on this. But we still had some academic standard to follow, even though we are entrepreneurs. So we did actually do a very in-depth research in the past few months with the help of a team. So I'm going to just start by sharing some of those high-level learnings and findings. And the key question for us was, where does technology come from? We are surrounded by technology. We have been advancing as society thanks to technology, but where does it come from? So we asked that question, and we try to ask, I guess, the most difficult question: how can we translate scientific innovation that is born out of some of the most fascinating R&D centers in the world, and is also a very understudied field? Those are the national labs. Academic spin-off has been researched for many years. We have a lot of examples across disciplines, a lot of success cases, from how Stanford was able to spin off companies like Google, to MIT spinning off about 30,000 companies since when it's born. But there is another category of research centers which is incredible from a technical perspective, and there is about $16 billion being spent of our taxpayer money to fund these R&D centers, and those are the national labs. So I'm going to just go very, very quickly, and I'm going to show you some of the high-level findings that the team has want to present. And there's going to be a report that we're going to publish. It's going to be a Harvard publication in the next few weeks. So I will share with you all the final report, which is a long and more elaborated products, but we wanted to just give you a sense here. I'm going to go really, really quick. So here's the team. Happy to work with Heather and Philip. They were my research assistant for this project, and I couldn't have done this work without them. So thank you, Heather and Philip, for your contribution. So the main question that we ask, going back to what I said before, is where does technology come from? And we had these key hypotheses before we started the project. The first one was that there is a lot of innovative technology. They have a lot of potential to have an impact in society that have been developed today in national labs. At the same time, we feel that national labs have a mission to develop those technology in the world and spin them off, but they're not doing it in great numbers, like what MIT or other schools would be doing. So if it was zero, it would think that they're not interested in doing it. If it was a lot, we would think that they're doing a lot of work in the area, but at the same time, there is a few number of them. So there is an interest, but there is not a system that is well developed. That was an hypothesis that we try to validate. And the third thing is that we believe that because of different reasons, because of the nature of the national labs and their obviously history, they're in need of an upgrade. Universities originally were not meant to spin off companies, but now they are. And every university around the country is trying to do that, right? So national lab also are not meant to spin off company, but maybe there is room to propose some policy changes that can actually influence that and making those labs a sort of innovative spin-off. So why do we look at national lab is because, again, as I said before, university have been overstudied. There has been a lot of research on the impact of academic spin-off. And here, with FIO, we have an example of FIO spin-off coming out from his lab. But we felt that there was a field that was very, very well studied. So Secretary Carter was very, very keen in trying to push the research into the areas that are not studied and that were not very clear in terms of how do we build company? Can we even do it? So that was the initial question. And in terms of sorts of innovation, we have national labs, there is university, companies actually are doing a lot of research now, and then there is private organization like foundations and philanthropy. So we decided to focus on the national lab for the scope of this research very, very quickly. I mean, there is 42 national labs, they're scattered around the US, they're funded by different agencies, and 13 agencies are funding them with taxpayer money, and they've been built around the 30s and then in the 40s and the 50s post-Cold War. I mean, those labs have been instrumental to maintain and sustain US global prominence in science and technology. So people might say their role is not to spin off companies, and we agree with that. That's not their primary role, but we still believe there's room to address that. And just take a look here at some of the things that we would not have if the national lab didn't do this research. I mean, they discovered 22 elements, right, of the periodic table. 22 elements wouldn't be here without the work of researchers there. And obviously, we try to emphasize the need of policy also to use some of those scientific discoveries in the most responsible and public purpose way. I mean, the DVD, for anyone that still remembers the DVD, I mean, it's been created in some of the national labs. I mean, we don't have the DVD anymore because more innovation is coming. So this is a refresh, continuous refresh from some of the technologies that they were seeing. DNA was decoded. National labs made airplanes more resilient. And to just give an example of something that was very useful in the Fukushima disaster, some of the technologies developed in the national lab were actually used to clean some of that water. So this is a very good example, I think, of a good use of those discoveries. Also, national labs really continue to advance some of the most critical areas that are highlighted by the US government as the most important area to continue to fund, from biotechnology, advanced computing, human machine interfaces. Here we put some list of those capabilities that the government is prioritizing. This is from the Office on Science and Technology Policy at from the US government. So here, just a map very, very quickly again, 42 labs. Look at the spread, right? Some of them by design, in fact, are in some of the most remote areas. And it's quite fascinating to see that there is a potential to build local ecosystem around some of those scientific labs. And the funding, I was touching on that before. Here, just we break down some of the appropriation and funding that are allocated to the national labs. And you can see that each agency has different approach to this, but Department of Energy, NASA, Department of Defense are allocating billions of dollars every year to keep the lights on in this national lab and continue to advance some of the most interesting research that they fund. At the same time, they also are able to get different sponsor and work with industry and have collaboration. So I think the national labs are really advancing a lot of this research that historically has been funded, again, by the different agencies, but also by different companies. If you look at the numbers of people, that's why I was interested in this concept of local economic development in some of those remote, if I can call it like that, areas. Los Alamos National Labs, 11,300 scientists, right? So you look at some India National Labs, you look at some of the labs that are even like in Idaho, you have 4,000 scientists, 4,000 people working in the area. So the impact is huge on the local communities and in the local areas where those places are located. And our hypothesis was that if we can enable a portion of those technology to be spin out from those labs, create companies, people can create more jobs, they can attract more funding, and then you can create ecosystems around those research centers, similarly to what MIT has done with Kendall Square. We look at what they're working on, and those national labs are really mapping well in what we call the deep tech ecosystem. So we think about biotechnology, advanced material, advanced engineering, photonics, electronics, nuclear physics, space, you know, you name it, artificial intelligence. So those are all the things that those labs are working on. So we feel that there is a very large, you know, potential here for deep tech entrepreneur to leverage some of those discoveries and advance them to the point that they can be commercializable. Here, I think I wanted to spend a little bit of time here because this is, I guess, one of the most interesting part that I consider of this research that Philip, Eder, and I have been working on. So here, what we try to do, we try to provide a map for people like me that were interested in starting company with science. And there's a lot of people that realize that if you want to be an entrepreneur, you have to look a little bit beyond what is the problem in front of you. I was born in a small town in Italy, and I didn't see some of those big problems that I was trying to address, like how do we make vaccines more accessible, right? I mean, I didn't think about that problem. Like those are not the things that they were in front of us. And entrepreneurs tend to try to solve problems that they face in front of them. So if you want to try to solve bigger problems, they have an impact on human health, food and agriculture, climate, talking about like making industrial products more resilient and more green. I mean, even defense and security, you have to think about how do you work with scientists and science to leverage some of this innovation that has been developed in those labs. And sometimes this research, like in the case of the work that we've done with FIO, has been research that was years in the making before we are able to spin off a company. There was a lot of government funding going into this university to try to understand some fundamental and cutting edge technological potential of, in our case, silk. So here, what we did in this map, we tried to, provide a map, and it's going to be in the report. So please check it out when it comes out. That is trying to map different functional areas. And by functional area, I'm talking about the deep tech, I guess, areas like biotech, advanced material, nuclear physics. And then we took a slice of that because we felt that we were more, I guess, expert around the biotech, advanced material, and advanced engineering. So we tried to map it out against different use cases. So for example, if you think about using a new material for food and agriculture, you can look at Pacific Northwest National Lab in Washington State that has a very, very strong expertise in the area. If you're thinking about, advanced engineering and industrial goods, so this map provides a very high level map to orientate yourself to try to figure out how you can advance some of those technology to market. And then, we spent some time to put a little bit of a blueprint of a guide on how do we actually do it. And that's largely based on our experience as entrepreneurs working with scientists. And so we provide that in the report, trying to really encourage scientists and entrepreneurs to work together. And we try to identify some of the best practices. So then we analyze like why spin-off is important, and there's a lot of research around that. So I'm not going to spend too much time on that. And then the gaps, right? We spent some time figuring out what are the main gaps that, why there's not a lot of technology transfer from those national labs. And there is a lot of things that we don't have a lot of control on, but we still wanted to provide some policy advice for policymakers to try to figure out how to address some of those. We look at some case studies. I mean, the Lincoln Lab is a great, I guess, not really apple to apple, but it's an interesting comparison because it's also in Boston. It's quite, in the ecosystem of MIT. So we look at that as a case studies. We try to map out the different technologies and different companies that come out from the Lincoln Lab. So at the same time, we look at the other coast. We look at the Pacific Northwest National Lab, very strong on catalysis and chemistry as a heritage, I guess, from that lab. They have really a lot of effort in the commercialization. So we talked to the different directors, and actually we talked to the director of the technology licensing office, and we discovered that they're really putting a lot of emphasis in trying to spin off companies. So this is part of their mission. We also look at some of the success cases. This one is my favorite one. It's a company in California that is harnessing the power of waves, they had a lot of success leveraging funding from Department of Energy and collaborating with Oak Ridge National Lab and with other labs. And yeah, so this is kind of the high level perspective. And I wanted to highlight before we move on, one initiative that we identified as one of the most high potential that we suggest to be scaled up greatly. So this Co-Activate is a fellowship that is a non-for-profit organization that supports scientists to transition toward entrepreneurship. So they would support you for 2 years to work on a specific technology, whether it's a national lab or not, doesn't matter. But there's been a lot of work done with the Berkeley lab in California, and now they're doing a lot of work with the Lincoln lab. So we spend a little bit of time trying to understand their model, and we think it would be a very good model to have scientists/entrepreneurs to be embedded into the labs. And so that's one thing that we wanted to highlight. Also, we figured out that there was a big lack of private funding and venture capital funding to go specifically into the national lab technology. So we suggest and recommend that there would be a fund that would fund some of those research, and early stage fund that would put some money into early stage company trying to address some of these big problems. So I'm gonna stop here. Again, I will make sure that the report is shared with people, and if you're interested, please do let me know. And now we're gonna move on to, I think, the more interesting part, and I think this is gonna be a interesting discussion. So first of all, Fio, thanks for joining us today, and thanks for work with me for all these years. I think it's been a great pleasure. It's been more than 10 years now. But maybe to get us started, can you give us? You've been in both. You've been in national labs. You work at Los Alamos. Now you are leading the research at Tufts University, one of the leading research institutions in the country, and you have done a lot of spin-offs. So maybe can you give us a little bit of flavor in terms of the main differences that you see between your work, at one of those national labs, and then the transition into more traditional academia, and then just maybe even for the group here, give us a little bit of sense of your research that obviously it's spanning different areas, and I think would be interesting for the group to learn from you.
Well, thank you, Livio. Thank you for having me. It's that's many questions. That's yes. Many questions in one. I think so. For those of you that don't know me, I've been at Los Alamos. I worked at Los Alamos for almost a decade, for 8 years, and before coming to Boston. And I think that the comparison is somewhat unfair in a way, because comparing the environment of a national lab and with a university in Boston is already a bit of a skewed playing field, because Boston is unusual and is very rich in technology and entrepreneurship. So there's a vibe here that I think you find in only a few places in the country, if not in the world. But I mean, by broad strokes, I would say that the environment of a national lab, especially Los Alamos, as you pointed out, was probably the one that had the highest density of scientists. There's a very deeply rooted scientific core and very high technical expertise. What happens because of the mission of national labs is, I think, that the inertia is a little bit higher. So it's not that people don't want to innovate. It's more that there are different steps and different, maybe for compliance, even for selection of intellectual property filing or assignment of rights. The procedure is a little bit longer than what you experience, for example, in a university, where these things happen very fast and there's a technology transfer often, and then these things are becoming more, part and parcel of academic life, is to try to take some of the technologies that the university has and develop it. I mean, there might be also a revenue model that is different from the university than there is from the national labs. But I can tell you that I did go through the process of filing intellectual property while I was at Los Alamos, and we did go through the process of thinking of starting a company, even and companies back then. And it was just a longer procedure, and you kind of lost a little bit of the, if you will, of the immediacy and of the momentum, and then you were in an environment where certainly maybe attracting investment funds was a little bit more challenging, and you had to maybe go a little bit further to find your seed. So I think overall there is this disparity, and certainly I agree that there are a lot of very impressive technologies that come out of national labs. I mean, for sure, the talent is immense.
And then, so in your transition from there to Boston, I mean, how did your research evolve? One of the learning that, we talked to a bunch of professors that are involved, for example, in Lincoln Lab and then at the MIT, and one of the learnings from them was that they have much more creative freedom in the academic side. You can play around with more creative ideas, while in national labs there is much more kind of like a mission-driven project that it needs to be kind of executed. So do you have any thoughts on that?
I mean, yes, plenty, in fact. But I mean, but maybe again, it depends on context and circumstance. And certainly the idea of deterrence, which is certainly one of the you could argue that this is something that Los Alamos, at least, was stewarding for the nation. So there is clearly a very deep nuclear root in Los Alamos's history. So the mission is driven historically by that, but also in parallel to the deterrence that you may have from something as very socially impactful and sort of globally impactful, like the nuclear arsenal and related things. There is also a scientific deterrent, and having the capital of very capable scientists that are able to address very complex problems at the drop of a hat is a very important thing that I think that national labs have fostered for quite some time. And so there is a mission-driven part, but there's also a more open investigation that is based on scientific quality and that is not necessarily as tied to the mission. This is something that was called, and I don't know, maybe it's still called, the laboratory directed research mechanism, which is a portion of the budget that is allotted to the lab that is dedicated instead to free form research, and goes really to efforts in biomedical imaging versus in nonlinear optics and communications and things like that. So these LDRD funds were really sort of like the free form research, if you will, in a national lab environment that I would argue would give a lot of intellectual freedom to do research. I certainly thought that I had a lot of very interesting avenues to pursue while I was there. Then, of course, in general, you are more your mission is you're mission free when you are in academia. But I think that there's a balance also in national, or at least in certain national labs there is. I don't know that it applies to every single national lab. I would say that in general the statement is true, but I would not underestimate also the power of very broad thought within the national labs. I mean, some of the best, kind of like traffic management algorithms and kind of like nonlinear dynamic, kind of like nonlinear management of flow of transport optimization came from Los Alamos, for example.
And I think, yeah, that kind of reinforces the concept of like, how can we accelerate some of that transition? And, people talk about deep tech and deep technology. So my argument is that if we really want to uncover deep tech, we should look at some of those places more, and we should have more mechanisms to have those technology translated into lab. But for you, it was more like only until you came to academia that you actually started to operationalize some of those spin-off concepts, right? So how did that happen? I mean, can you tell us more? How did you start? Because you were doing physics, and then you transitioned to this more like interdisciplinary approach, which I think some of those universities really encourage, right? So you were in a biomedical engineering department with a physics background, and what happened there? Like, what did you stumble upon, I guess?
Well, I think to be completely honest, and I mean I don't have many deep explanations about this. You kind of are always driven, in the world of physics, applied physics and engineering, to think about application and optimization of the things that you do for systems. And in a way, these were the things that we were doing when we were doing optics and materials and things like that. When I came to Tufts, I guess that really my interpretation of what was happening at in a biomedical engineering department, where I kind of didn't really belong, was really with a technology eye that was driven by what I had done beforehand at Los Alamos and previously. And so I think when you kind of are looking for materials and applications of materials, then it's the step to actually imagine the future of an application in materials in different fields is not too far away. The thing that made it very very exciting, and still to this day exciting to me, is that the materials that now I'm using are not anymore materials that are developed in a crystal growing chamber or in a furnace or whatever it may be, or under high pressure, but now there are materials that are grown by nature and that are edible and that are implantable, and that still have a lot of the technological attributes that the other materials do have. And so that,
and to get to that point, it was like a lot of years. I mean, we're talking about like some fundamental intuition that some of those materials could have an application across fields that maybe no one really thought was possible, was feasible. And how did you convince, who was funding you for those? I mean, was the university, how did you convince people to bet on some of those approaches?
Well, I have to say, I mean, since this is a context about national labs, I mean, Los Alamos was amazing for me. And they were, and I will always have an infinite depth of gratitude to Los Alamos for besides for when I was there, but also because when I moved to Tufts, they donated my lab. They donated my lab so that I could take it with me to Boston, which was incredible, because it gave me tremendous runway to sort of be independent for funding for a couple of years and really explore what was next. So from my area to trying to see what the bridges were with the biomedical sciences. Then when you join a university, you always have some sort of startup funds, and so the beginning was really very very freeform. And then we did get funding. We got a very big grant from DARPA at the time to look at some of the silk technologies, and so that sort of accelerated a lot of these things. But really, I think that was what made it, is just the freedom to try to connect things and try to imagine how one domain would translate onto the other. And maybe sort of a little bit of I don't know, a little bit of serendipity, if they come and tell you, if you realize that suddenly every piece of technology that you can make can be implanted, or you can eat it, then you start thinking about the things that you've done and that you've studied for the past decade a little bit differently, and maybe that inspires different thoughts.
And I think, Phil, one other thing that I think distinguishes your approach that I was able to witness is your capacity to kind of disseminate some of those long-term ideas to the public, right? So in fact, for the benefit of everyone, I met Theo not because both of us are originally from Italy, but because actually we met online, because I saw his TED talk, and now he has more than millions of views, and it's really fascinating. And that was around 2007, 2008, or 2009, around that time, or 2010. And Theo was talking about how you could use Silk for a bunch of application, but so your capacity to disseminate those things, I think, was crucial to enable people like me to learn about technology when I don't have a degree in advanced, nuclear physics or optical or biomedical engineering. So I think that capacity to do it, I think that it's very important, that it can help to attract some of the other people that can complement your work. So maybe this could be an advice for other scientists on this meeting. But you have, any thoughts? I mean, that was deliberate, right? I mean, TED Talk is not very common that professors do that. How did you decide that that was something that you wanted to do?
Well, I didn't. I think
Okay.
they invited me, and I thought that it was a bit weird. And
You didn't seem nervous at all in the video.
Oh, I was completely nervous. Yeah, no, that's I completely was. It's very hard to take the stage, after, people from Hollywood that know how to take a stage in front of so many people, especially when you're talking about, your little world of light and stuff. But I think it's important. I think it's always important to be able to disseminate. And again, I mean, I think trying to it's very important to be able to answer the question, who cares? And this is something, that many, that a very, very particular set of very, very good professors ask you in multiple contexts, sometimes in front of an audience. After you're done explaining all, a year's worth of work, they will stand up and say, okay, who cares? And I think that it's very important to be able to know how to answer these questions, because generally that is the driver behind purpose. And purpose can take a lot of directions. And certainly one of the purposes can be to develop something that is good, as a product, that generates innovation. Another one can be just a pure question of scientific interest. But I think, that communicating why you do things and why you like doing things is incredibly essential. And then if these things become technologies, and become technologies that can be developed and that can have societal impact at some level, then I think that it becomes a very powerful message, because then it builds a lot of value, not only in what you're developing, but it builds value in an ecosystem. It builds value in appreciation of technology, of science, of discovery. And so it actually does, has I think a very long tail effect on building human capital, and on building a generation of contextually aware people that then will do very, very good. I saw a question actually in the chat about retaining public purpose, and I think that I have thoughts on this, but I think that this is one of the public purposes that you want to retain. I think maintaining technological excellence and bringing things forward has a lot of beneficial effect to the immediate surroundings, and perhaps statewide, and then nationwide and globally. And so I think that the public purpose of generating revenue, of creating jobs, of industrialization and services become very, very important.
And I think I have a next question, but I think I have an answer for myself, but I think it's worth sharing. Like, why your research matter? I mean, how did you answer that question when people ask you, like, you look at all these crystalline structures of these new materials and their dissolution? I mean, you went so deep into the years of research trying to understand something that probably like only a few people in the world you can count in one hand, right? Probably they understand it to that level. Why did that matter, and when did you realize that those things that were fundamental research were actually getting to the point that they were becoming more translatable? Was there like a specific moment? Was it a process? Maybe was it too early when you did it? Was it too late? Any thoughts on this?
I don't know that there's an answer. I think you tend to be very, I don't know. It's a mixture of purposefulness that comes from maybe experience, and then day-to-day reactivity, so to speak, to recognize maybe an opportunity that shapes. So, maybe I mean in my specific case, I suppose a lot of studies of nonlinear optics and materials and communications and fibers and semiconductors, have very, very beautiful physics behind it that is still quite beautiful, and I enjoy very much. I don't get to do much of it these days, but they also have generated a tremendous amount of technologies that are so deeply impactful across our world. I mean, we are staring at screens right now. We have ultra high bandwidth communications that are arguably generated by being able to control very, very short impulses of light that are carried through strands of fiber. So these are some things that there was always a tangible application that was attached to some of the fundamental research. So now, if you have these vectors of I can implant it, I can eat it, I can make it dissolve, and you know that you can replicate some of the devices that have been already used, say for example in photonics or in semiconductor science, and take that approach, then you're looking at technology in a very, very different way, but you're seeing kind of different types of applications through the lens of new materials. And so it's really a question of, what if you were able to embed, I'm just going to say something a little bit hyperbolic, but what if you could incorporate life in a semiconductor, and what could you do if you mix these things, and then along the way you kind of see what this new approach enables. I don't know. I think it's a little bit of the fundamental meets applied, meets a bit of pragmatism of trying to do something practical and meaningful, and that can scale also as well.
And so having these platforms, I mean, that's what everyone talks about, those like large technological pool of different technologies coming at the same time, at the same place. I mean, in your case, maybe we haven't spoke too much about it, but like, can you give us like the super high level about your research specifically on silk, and how the convergence of different fields came to kind of clash? I mean, from physics to optics to, you talk about implanting, so we're talking about, your human body, we're talking about physics. So that, I think that's very fascinating, and we see a lot of successful research effort that really now become interdisciplinary in nature. I think that's, and they build this large platform, and then you can slice it up and translate it into the different application. I mean, you've done 3 or 4 startups that are slicing up the same kind of technological area, but obviously with different applicability. So a little bit similar to our map when we think about how do you use advanced material for, in the case of agriculture, in the case of healthcare and vaccines and all of that.
Yeah. Well, I mean, the 3-minute version is that basically from textile material you can go backwards and get you get a biocompatible liquid that, for all intents and purposes, is a biopolymer, and so it's your starting material to generate that could be comparable to what you use as a starting material for plastics. And so if you imagine that the technological uses of something like that, but with a material that preserves whatever you mix, preserves the life of biological matter that you mix in it, that you can eat, that you can implant, but that at the same time you can reshape into into plastic-like materials, into ceramic-like materials, into hard materials, then you really open up a world of material science applications that is very big. And so basically I think that through silk and through biopolymers in general, my research is about making materials that bring the technological worlds and the biological worlds and the life sciences world as close as humanly possible. So really putting putting them together in materials that have extraordinary functions, biological functions, while maintaining a very large library of shapes, where the shapes can be large. They go from the nanoscale to the meter scale. So I mean, edible electronics, implantable sensors, distributable sensors that can be thrown in the environment and send data and then melt away when it rains, to coral reef safe sunscreen, to preservation of vaccines, to preservation of food, to alternative to volatile organic compounds, and and strong underwater glues that are made only with worm spit, et cetera, et cetera, et cetera.
So the technologies can get all this kind of permutation. I mean, the same, I guess, as we said, the technology base is there, right? And then how do you get to think about those other applications? That, some of them, it looks like you were thinking them on the fly, but some of them you have been working for years. I mean, the case of vaccines has been that, right? I mean, the fundamental discovery that you could combine vaccines and biologics with silk, it was, maybe not expected, but there's other things that, maybe you haven't found, you haven't thought about yet. And so this platform is not exhausted yet. I mean, where do you feel you are in that, applicability of this platform? I mean, do you feel like you have scratched the surface? Do you feel like you're at the mature point? And where does the creativity meets the technological need, right? I mean, those are the science and creativity. And one of the things you've been doing really well, and that I really love about your research, is that you have been working with a lot of interdisciplinary people. I mean, I'm talking not like you're a physicist and you work with a biomedical engineer. I'm talking about you're a physicist and you work with musicians, right? I mean, that's like, how do you, is that your sorts of inspiration to get kind of people across the table that maybe they speak a different language, or they play an instrument, or artists and designers? I mean, you have in your lab, you have some of the most interesting group of people that, they're walking around the hallways. And is that a strategy, or
I don't know if
it's serendipitous?
I don't know if it's a strategy. I think it might be interesting, and I think that that I'm lucky enough to have again, this is somewhat easier to do in Boston than it would be to do maybe in New Mexico, to a certain extent, because of the abundance of people from all walks of life that come through here. But I think I mean, there's two aspects of this. One is really the arts and the sciences, and I think, and the way of looking at a problem that one even though left brain and right brain is the wrong way to describe these things, but you say more more method driven person rather than more artistic driven person approach a problem. And so I think that there is a sense of aesthetics in the way that you formulate a question, where having people that come from different walks of life and talk to each other helps both sides. But I think even more importantly, I really do think maybe I'm a little bit of a universalist, and I think that people that really want to solve a problem and people that want to make an impact generally do speak the same language. There are these things that are common traits among certain classes of people that really want to to either make an impact, to be the best they can be, or whatever whatever metrics you want to use. But there is a distinctive characteristic among these people that sort of and sort of like a convergence of thought where you can put them in the same room and they speak the same language. And generally, after conversation, you find that the metrics are very shared. So the conversation is easy. I don't think that I don't like the word. I don't like the word interdisciplinary. I think that interdisciplinarity, as we talk about it, really is generated by people and not by putting close to physically close to different departments. It is, and there's many interpretations of this. I mean, it was the cafeteria at Bell Lab. It's always people conversing that find a way to do something interesting together because they really want to do something interesting in the end.
So maybe the Zoom format, we'll need to rethink about that soon. So hopefully next year we'll have those
Zoom
sessions.
Is slightly dehumanizing. Yes.
I completely agree.
A little bit. Yeah.
In fact, one fun fact about Theo and I, and going back to the theme of these unusual scientist / entrepreneur duo here, is that one of the first things that we did, I pitched this idea to Theo. There was, what about you come to Cambodia to see some of the silk farms? Because I used to work there, and it was, you didn't think it was weird, my request? I mean, I asked him to join, and it was great because we went to see some of those farmers that were in these remote areas, and they were supported by the United Nations to grow silk. And obviously, my naivete was the idea of this farmer can supply a lot of silk to Theo and his technologies. And then we realized that the first company we studied together, we probably only need about 10 kilos of silk in per year. So it's not a lot. So that was very naive. So we went back to them. We thought maybe there's other application in the food sector, and now there is another company that Theo co-founded that is using silk in very large scale to make food be more resilient. It's a coating that goes on top of the foods that is able to extend the shelf life. And now we're talking about tons, right? So that type of local impact that you could have on the suppliers, I think that's something that was always important to you and to me, obviously, because we thought that we could extend some of those benefits of how we use some of those technology developed here in the developed world in some of the best academic research institutions, but they can have an impact, I think, globally. So I think that's it resonates a lot. So I see there is 10 minutes left, so I wanted to make sure we give some audience to questions, and so why don't we open it up for questions in the Q&A tool, and then we're gonna try to address it. So I'm sure people have a lot of questions. So I think one you already kind of touched on the impact. I can just, as we wait for more questions to come in, I can give my take on that, which I think that's exactly the reason why we've been working on this project, right? I mean, I spent 10 years being an entrepreneur and building companies based on scientific innovation. I think one of the things that it's very important is that how do we define some boundaries around the public purpose that this technology can have and the shape that they can take, because they've been generated with a lot of public funding, right? If you think about it, as Theo said, DARPA gave him his first, Los Alamos gave him the lab to bring it to Boston, and then they gave him the funding from DARPA to advance some of the scientific discoveries, and at the same time this is quite interesting. So okay, so I see some questions. Okay, Francella. Hi, Francella, my friend. How are you? Yeah, are there any questions in your research project that you would like to revisit? Yes, there is a few questions. I think this research was really stress testing what it means to commercialize and spin off a company, because a lot of the technology actually they are classified and they are very, very sensitive from a national security perspective. So obviously there are certain areas that are not up for a spin-off, if I can put it like that. So I think that's a very important point. And so trying to figure out what area of research are more commercializable versus other, I think that's interesting. We have some anecdotal evidence around that in some lab, up to 40% of the research is actually nothing to do with military or defense or national security. It's really chemistry, it's really biology, it's really sensors and other things. So that's one answer to that. Any other questions? Otherwise, I have a few more for Theo, but maybe I ask you as we wait for other questions. Oh, maybe there is another one here. Okay, Stephen, why do you think that there isn't a VC fund community focused on national labs? Did you get any insight from VC? Okay, good question. There's been a lot of new VC born around the concept of deep tech. The engine is one. In fact, they invested in Vaxes and invested in a couple of other Theo's efforts as well. I mean, I think there is more understanding that those technologies take a long time to develop. So I think the main issue for the VC is really the timeline, right? I mean, some of those technologies can take 10, 15 years to develop, and VC usually they have a shorter time frame. But I think there is a lot of changes in this because VCs are starting to understand that if you want to address some of those big societal challenges, like transitioning to a clean economy and fighting the next pandemic, you might have to invest in scientific technologies. And I think scientific companies could address those things. And if they're willing to wait, and we heard it from various VC, like the engine, we have Katie Ray that was here with us in a panel. And she was saying something like, we're willing to wait, but we want to have a huge impact, right? So they've been catering to different investors themselves that have a longer time span. So that's one. Okay, I see another question. Do we need to move away from a national? Okay. Do we need to move away from a national lab model to establishing government business collaboration space by default, or is there a value in maintaining government-only spaces, especially for early fundamental research and complex societal challenges? I'll give you my take. I think there's a point in which you need to make a clean break between the academic research and the funded research by the government and the transition to a private entity. And I think there's a process for that. My feeling is that it's important that that break is pretty net and pretty clear. And I think venture capital money can really help you to formalize a lot of the processes and put a structure in place that I think can help you to scale. At the same time, I feel like that you can continue to collaborate with the public sector. There's a lot of potential grants that the government is willing to give to companies trying to address, for example, energy or healthcare challenges, especially if there is, technology that are early stage that they can get to the point that now they can be ready. And now Laser is asking about the policymaker. So I think what the policymaker can do to facilitate the commercialization of deep tech. I think we put a lot of effort in answering this question, and then we realized that obviously those are recommendations that we don't have a direct impact in, but I think we wanted to highlight them in the report. So thanks for asking that question. I think there's a lot that can be made, and there is a lot of efforts underway. There are a lot of small scale pilots. I think a lot of people like to do pilots, which is nice in a sense because you can test and iterate and see what works, what doesn't work. There is a couple of things that is very interesting in which the national labs are opening up themselves to entrepreneur. Especially Los Alamos is doing that, Oak Ridge is doing that, Sandia Lab is doing that. So basically they're allowing external people with an expiration date on their back, because one of the main things we learn is that scientists in national lab want to stay in national labs, right? There's not a lot of flow from national lab to industry, from industry to national lab. It's very much like a career that is pretty set, it's pretty stable, and you don't see a lot of flows. While university, Theo, correct me if I'm wrong, but like you want to get your PhD and your postdoc out in the world as soon as they can, right? As soon as they are ready. So there is a cycle, there is an expiration date that you put on those people, quote unquote, so they can actually go out in the world and bring some of this technology forward. So I think those are some of the things that I would say. And I think, yeah, if you were able to answer some of those, maybe in the last 3 or 4 minutes that we have, I'm gonna have maybe one last question for you, Theo, that I think, I don't know if you have an answer for that, but what was your biggest challenge in working with entrepreneurs? And I don't take it personally. I know. But like, you know, obviously there is different incentives, and you're judged in a different way. You have your papers to write, you have your grants to get. I mean, how did you, and we didn't rehearse this, so you might say something new here. But like, I'm just wondering about like, how do you see that that tension sometimes, and you know, how those things can be, you know, facilitated. Maybe there is some policy idea that we can come up with based on that.
Well, I don't know. I mean, I think there needs to be sort of like an awareness. I think things work well when both sides are very aware of what the other side does. And that means that, you know, that the scientist doesn't have to expect that because it works in a lab, it's automatically a product, or because it's the fruit of a lot of years of work that's going to lead to you know, to revenue, and vice versa. I think that the entrepreneur has to have you know, there has to be very savvy about the limits of science and research and technology. You know, it's kind of like not expect that all the answers, the technical answers will be solved in the lab because the lab is there to solve them. I mean, I think that that's the main, you know, those are the main disconnects in these things. So there has to be a healthy dose of you know, of pragmatism and of ability to recognize the other contexts from both sides. And I think that usually the difficulties that one has are when there are unrealistic expectations from either of the two, whether it's you know, whether it's on development times funding, you know, I don't know, and the you know, whole litany of things that are typical of developing these things. So I don't know. I mean, I think it's you know, there are two worlds that have to talk to each other, and generally when they are able to talk to each other and the two expectations are met, they work well. When they don't, they usually that's where you don't even get past the seed, if you even get to the seed, right? So
And that's yeah, that's why we wanted to have the discussion. I think I hope it was beneficial for the group, mostly because of what you just said. I mean, to show that this is possible. Those are two different worlds, but they actually can collide and can build on each other expertise. So I think that was the message here for this session. If there was one takeaway, I think is that working with scientific innovation is possible even for people that, you know, I didn't have a scientific background. So I think that's an important lesson learned here. And the work on National Lab is really trying to encourage people to look at the boundaries of where does the technology come from. And those are the places where you should look at. You should look at the source of innovation, and then you'll find potentials to have a big impact. So I think that's the main takeaway. So Pio, thank you so much for being here with us, with the group.
My pleasure.
And I want to thank all the participants from all the different countries. I see a lot of new faces and names. So and I want to thank the, you know, TAPP and the Belfer Center, Rita and Karen and Secretary Karen and Philip and Eder for helping me to get to this point. And hopefully that was helpful, and we'll share the report with you guys and everybody. So hopefully we can go a little bit more in depth if you're interested to learn more about this. So it's 3 p.m. We're right on time. So appreciate everyone's presence, and thanks again for joining us. And I hope to see everyone soon.